Thank you. Yeah, so my name is Jan van der Vecht. I worked a lot as a data scientist, more on the machine learning side. I don't know where I should stand. On the machine learning side to, well, directly solve business cases. But over time, I got more interested in more meta things, which includes proper experimental design, but also industrialization of machine learning models. And a part of that, of course, is to have a proper experimental design because you want to make a decision based on how well you're going to do in production environment. So my company is called Kubernetes. We are mostly focused on industrialization, but that's not the talk of this or the topic of this talk. So we're going to talk a bit about how to properly evaluate how well your model is going to do in a production environment, or how well you can predict something in a fair way. So first we're going to talk a bit about the problem statement. We're going to talk about generalizations. It's a bit of a more theoretical topic maybe than the other talks. We're going to talk a bit about certain assumptions that we usually implicitly make, but that can have a very significant impact in how you have to evaluate your performance. We're going to talk about a number of different validation schemes and the up and down sides of these, and why we choose certain ones, and why we even do this. And then there's some small other pitfalls that you can fall into that will make you over or underestimate your performance. So the problem statement is, let's say we have built a model. That model has been chosen over a number of other models. It's for any type of case. And we're interested in knowing how well this model is going to solve our task. This is very important because we usually have to make a decision whether we're going to actually use this model, whether we're going to invest time and money into using this model, or to maybe help more on the research side to help the society further. This is very important. Quite a recent example where this went terribly wrong, and it's not even fixed, is last year a number of researchers said they could solve predicting earthquakes by using deep learning, but they had a very severe leaking problem where there were basically similar training samples or the same training samples in their training set and in the test set. And there were very bold claims made based on that. It went viral, and this was published in Nature. So this is a very difficult problem. A lot of people make these kind of issues. Even Nature publishes these kind of mistakes. So this is an example of why it's important, but also that it's very common. So I'm going to explain a little bit about what is generalization, starting from a more academic level down to a more industrial or pragmatic level. So the more academic definition is about how well does our model adapt to new, previously unseen data drawn from the same distribution as the one used to create the model. And then it goes, okay, how well does our model predict on unseen data? How well is our model going to predict in a production environment? Or maybe your manager, how much value is this model going to generate? So this is kind of the question that we're interested in. So we want to try to simulate how we're going to actually use this, and that simulation is part of, or the reason of that is to see how well we're going to do. So if we use this definition, we can look at a kind of a formula which is based on it's called the generalization error. And it basically comes down to, okay, we have this joint probability distribution of your feature space and your target space, so your input and output. And we're kind of interested in, okay, we have this model Fn. We put in our features, out comes output, and we want to measure how well that does over all possible combinations. So this V is basically your loss function or your metric of what kind of mistakes you're making. But of course, this is not, we don't know this. We cannot know this. If we knew this whole probability distribution, we wouldn't need a model. So, but we're very interested in this because this shows how well we're doing. So how can we do this? We could instead kind of approximate it, or because we do have access to samples from this probability distribution. That's our training set or our data set. So if we take a number of these individual samples, we have trained a model on different data, and we measure how well or how poorly we're doing. That is kind of an approximation after we average it of this initial definition. So that you can see that here, this is an approximation of this with some kind of error term, which is introduced by the sampling. The expected value of this error is 0. That's important, and that is the case because we take this sample. In reality, this is not 0, and that's because of other issues that we'll talk about later. So what we can then do is we can split our data set into 2 pieces. Most people are familiar with this. You have a training set, and then you have a validation set, where your model sees the training set, and then we feed the validation set to our model, see what it predicts, and then calculate this V, this error that we're making, and use that to base our decisions on. So I want to do a quick thought experiment where I will show that this validation is very good for doing model selection. So if we're going to do a number of models, and models could be different algorithms, different hyperparameters, anything that makes a difference. And we're going to use this validation set to do our model selection, choose which model we're going to use, which this is very good for, but that we cannot use that same set anymore for actual performing or model performance. So go to your manager, say we're going to make this amount of money. And I'll show you with this thought experiment, I'll hopefully show you why. So let's say we have a bunch of points, and we're going to do a linear regression. Normally you would have your training set, you fit this line either directly using some analytical properties or using gradient descent, and we're going to find our optimal fit. We're not going to do that now. What we're going to do is we're going to just sample random coefficients, A and B, and then see how well it actually does on this kind of unseen data. So we have some metrics, or the mean squared error. Well, in this case, it's the sum, but let's say it's the mean. And then we're going to sample these lines, and we're going to see how well we do. So we have a line here, A and B, and there's a certain mean squared error. So we take a number of these lines, and then we can look at our validation data or our validation set to see what is actually our best performing model. So, well, that's clearly the second one. But the way these models are generated are exactly the same, right? So even though we didn't use any training data, it's the same if we have a bunch of models that use the same training data, they all get a certain outcome. So in this case, the expected error that we're making for all these 4 lines before we actually draw them is the same. But we're going to use our validation set to see which one actually performs the best. And that basically means that now we've turned our validation set into kind of our training data, because we are using feedback or from our validation set to draw information about what works better. And that's an important concept, and that's why that's why we actually need a test set. We'll get to that a bit later. So here, let's say we have the same experiment, and we're just going to draw random models, and we're going to see how well they work. So we have this is, let's say, our mean squared error. So the blue line is kind of our expected mean squared error. And then, so we've drawn 6 samples, and this is the model we end up with. If we then look at this formula that we've done, our expected value, this blue line, is kind of our IFN, the one that we're interested in. But the sampling error, or the way our model is trained, whatever, the expected one was the same for all these models, but we chose the last one. So this will lead on average to the best model, depending, of course, on average, most of the time we're going to choose the best model, but it's not a fair evaluation anymore. We cannot use this mean squared error anymore to tell our boss, like, oh, we're going to do this well. And that's because the way we kind of do this selection, we introduce a selection bias, which means that the expected value of this error is negative. And that means that we're kind of overestimating how well we're going to do. And that's because we're using this kind of random noise in there to do our selection. So that's an issue. It's not an issue for, well, your first purpose, which is to find the best model, but it is an issue for kind of predicting how well we're going to do in a production environment. So that's why this concept of a test set is. So we have a bunch of different models. We split this data in the training set, a validation set. And as you can see here, it's not really unseen anymore, right? Basically, if we see this whole model selection part as finding the best solution, then we're actually seeing this data but in a more indirect way. So if we do this, we check what is the best validation score. That's going to be the model that we select. And then we have an actual unseen test set that we're using for performing like what we're going to, how well we're going to be doing. And the expected error of that one is 0 again. So that's kind of what we want. We want an unbiased estimate of how well we're going to do. So the problem of splitting our data in 3 pieces is that, well, all of a sudden we have a lot less data, right? Like, and that's okay maybe if you're working with hundreds of millions of rows, but if you have, say, 10,000 rows, all of a sudden it becomes a big impact in your data because, all of a sudden you have less. And sometimes people ask, okay, how big should my validation set be, or how big should my test set be? Well, that's really about what is your goal. So there's a kind of a trade-off there. Your training set should be as large as possible because in the end we're going to train our model on all our data. So the larger the training set during your validation step is, the closer it is to your real case. But your validation set, if it's smaller, you're going to have a larger variance in your estimate, and that means you're more likely to choose the wrong model. That's the same with the test set. Although you're not using it for model selection, you're using it to explain to your manager how well you're going to be doing. So if that one is too small, there's going to be like a larger range of what the actual value is. So one way to kind of solve this issue is by using something that most people are familiar with. It's called k-fold cross-validation, where we're basically splitting in this case, what we had before as a train and validation set. We're going to split it in the number of folds, and then we're going to train every model that we want to be able to choose. We're going to train it 5 times, each time on 80% of our data, and validate it on the other one. So there's kind of a trade-off there. We're using more data for we're using more data, so that's good because we have better estimates, so lower variance. But we also have to train the same model 5 times, which is going to be more compute intensive. And then after we've done this for a number of models or a number of considerations, in the end we choose the best one and use that for our test performance. You can go even further with this, and that's where, because we still have this test set that we're not actually using, and that's safe, that's nice, that's what we want. We don't want to use our test set to do any model selection because that defeats the purpose. So but if you still want to have access to all your data, you can do this concept called nest cross-validation, and this is even more extreme. So this first iteration looks very similar to what we had before. We're going to do cross-validation on our training set using all different models that we're interested in. Choose the best one, and then see how well it does on the test set. Then we're going to have a new fold, the next fold, with the test set somewhere else. And we do that so that this way we can use all our data, and all our data is useful for all these 3 purposes. But a really big thing here is we are not allowed to look at the test set to see which model we're going to use. Right? So because that's our sin, that's the thing that we're trying to prevent. So how can we do this then? Well, we're going to look at these hyperparameters, or this cross-validation. We pick the model, the performance is 4.5, and then we're going to do the same thing for the next one. But if a different model comes out, that's okay. We're not interested directly in our model performance, because our model is basically our whole set of possible models that we're considering. So we're just going to we're going to evaluate how our model selection what it will lead to. So in this case, there might be a different model that we choose. That's fine. We're then going to use that one, and then take the last one. That one might be model A again, and then that means that on average, our selection algorithm, or the way that we select our model, will end up on average unbiased with an error of 3.5, whatever it is you're interested in. So now I want to talk about an assumption that is very common, or actually kind of required in machine learning, that everybody is implicitly or explicitly aware of, which is called IID. It's a very common statistical thing, and it's very important because you're trying to estimate in an unbiased fashion how well you're doing. That means you kind of need this. So what does it mean? It doesn't mean that your X or your features need to be independent or uncorrelated or whatever. It also doesn't mean that your features and your targets should be uncorrelated. If that's the case, you don't need to do the machine learning because there's nothing to learn, right? So what it does say, it's about individual samples of your data. And that the identical part means that every row should be from the same distribution. So that's kind of an assumption that it doesn't hold true very, very frequently. And the independently part talks about if you know about a certain row, that doesn't give you any additional information about the other row. So there, it doesn't influence each other. Yeah, those are the kind of properties for that. So this is important for a few reasons that we'll go over now. Because you have these validation schemes, so this k-fold cross-validation, for example, where we actually sample data throughout your whole timeline. So, and time is often a common reason why this IID property is not valid. Because over time, some properties might change. The world is changing, right? That could be anything, like customer behavior. If you're doing computer vision, maybe, and you have 10 years of data, over time, cameras are becoming better, so they're more sharp. Or there's all kinds of ways how over time your data, either your inputs or your outputs are changing. So these kind of drifts are, yeah, those violate those IID assumptions. But that's okay. We need to deal with it. We cannot help that. But being conscious about it can help you figure out maybe there's a better or more fair way to evaluate these things. So the problem here is that if we look here and we have this k-fold cross-validation where we have the third fold as a validation set now, we're kind of interpolating in our data set, right? We have then, if you look at it from a simulation perspective, in the past we have data, in the future we have data, and we're trying to say something about things in between. And that's not fair, because if we're going to use this in the future, that we can always only look at data from the future. And then we kind of have to extrapolate. So this is maybe not a fair way to do this kind of simulation or estimate. So we kind of, if we believe that's an important thing, then we should only look forward. We should only use actual historical data and look forward. So another way of doing kind of a validation scheme that takes that into account is called kind of like a time windowing approach. So there you kind of still have these folds. We still want to have this property where we can use a lot of our data for validation, but we just have these folds and we only take the data that's before that. Yeah, so there's plenty of packages available. I think Alexander worked on one a while back. There's a lot of people that have built these kind of validation schemes, and they're very important because these kind of things can help you prevent making mistakes in how you think you're doing. But in that sense, there's kind of, because of this IID assumption that is broken, there's kind of a trade-off usually, where on the one hand, you always want more data, right? The more data you have, the better you can learn complex relationships, the deeper networks you can use, the deeper random forest you can use. And yeah, but on the other hand, if the world is slowly changing, there's a certain moment where data is so far away from your current status that adding that data is actually going to make your model perform worse. So and there's kind of a trade-off in between finding this kind of optimal threshold of, okay, we're going to look this far back, and everything before that is going to be discarded. And you should consider this to be a hyperparameter of your model, of your approach, where you can just say, okay, we'll use 2 years of data maximum, and everything before that is discarded. So that's a thing that you have to evaluate how well that works. But that also influences this validation schemes, because all of a sudden it's more like a sliding window over your data. Another bias, and this is one most of the talk is about overly optimistic estimating your performance, but one that you're usually underestimating your performance is by having a training size bias. Well, of course, what we're doing is we're trying to estimate how well we're going to do in a production environment or how well we're going to do in the real world. But after we've established that, we're going to train our data or our model on all of our data. That means if every time we're taking away a bit of the data, we don't train on the same size as the real model. So there's in that sense, there's kind of a bias because you're going to have more data available. So one way to kind of be able to say something about it, although it's not as rigorous as a lot of other things, is where you can look at, okay, what if we increase our training size? Like, how does that kind of our performance go if we keep growing our data size. And that allows you to say a little bit more about, okay, if we then go from 80% to 100%, how well does that do? Another approach, if you do think there's this kind of maybe like concept drift over time, the data is changing, you can also just, if you only want 2 years of data, you can just shift everything forward, and then there's no problem in that regard. And in another case, if it is still growing, there's probably you're going to do better than you performed. But if it's already flatlining because there's a lot of diminishing returns, then there's a big difference in those two. There are some more common issues that are related to this IID assumption. One is that is pretty common is duplicate records in your data. That's not necessarily a problem. It could be there's a lot of processes that actually do generate like separate events that have exactly the same representation. And if that's the case, then that's not a problem. But what is a problem if it's because of error from whatever IT system that you're using or sensor issues? Because then all of a sudden, if it's representing exactly the same thing, then if you are going to use random splits, you're going to have the same sample in your training set and in your test set, and then that's kind of like you're evaluating part of your training set. So if this is a frequent error, and this is part of your exploratory data analysis plus understanding basically the data generation part, so what kind of process is generating this data, that can help you kind of figure out whether you need to deduplicate your data, or if it's true, then you shouldn't deduplicate, right? You're trying to get as close to the real world. Another issue is a concept called target leakage. There's a lot of very direct ways where this can go wrong, but also the more dangerous ones are the implicit ones. So there's let's say we have a small data set, and we're doing some kind of feature engineering, but we have to split our features from our targets, right? So this is one that I've commonly done. It's fortunately one that's very easy to see once you've trained your model and you're evaluating how well you're doing, because you're gonna have no error. Because what happened, we forgot to remove the target column from our training set. Well, this should give you a lot of alarm bells if you get 100% accuracy. Then there's clearly something wrong. But there's a lot of more very more subtle ways to do that. This one is only applicable for larger data sets, where you have, for example, a categorical value or categorical column that has a lot of a high cardinality, which can be difficult, right? You need to represent that in a kind of a numerical fashion for some algorithms. And if you need to one-hot encode, if you need to have one-hot encode 50,000 different values it can take, well, that can be an issue. So one way of doing that is kind of using a type of categorical encoding thing. And one of them is where you try to describe, okay, this value of this category has this kind of target attached to it. And this one is pretty common. It works quite well, but it's a very tricky issue with this approach, is where if you look at this, so we're going to say, okay, category B on average has 1 as a target, category A on average has half as a target. That's correct. But if we're looking at a more how are we going to actually use this, then we don't know what the target is, right? So by doing this, we're kind of in a very subtle way leaking information about the target that's corresponding to this row into this encoding of this category, which is going to mean that the model will pick this up, and all of a sudden your targets or your training data, how you process this, is not from the same distribution anymore as what it's going to be like in a live environment. So what it should be is that you look at all the other category A's except for your current one, because that's how you're going to also encode them when you're doing it in a live environment. Okay, so there's a few takeaways. Oh, one more thing I want to actually say about the leakage. One way because this is usually happening in kind of more complex pre-processing pipelines. So one thing that is highly recommended for this is to use actual things like scikit-learn pipelines, which only get to see your training set and doesn't get to see the validation or the test set yet, although that's sometimes not so easy to accomplish. And one cool trick to see whether that's actually happening in your pipeline is to after you have your set, you just shuffle all the targets at random, because then there's no signal left anymore, right? So then if you have to do, I don't know, do classification and you get an accuracy that's, let's say it's balanced, and your accuracy is all of a sudden it's 55% over a large sample, there's probably something wrong. That shouldn't be the case. Your model shouldn't be able to learn anything because it's random. So that could be that's kind of a good way to kind of see if something like that is happening. And these kind of things happen with these kind of categorical encoders, but also with kind of more time series based things where you're using lag features. That it could easily happen that you accidentally somehow include some information about the current target. Yeah, so takeaway, you should really see cross-validation or what kind of estimation you're doing as a way to simulate real life. You're interested, your goal with validation is to find the best model, and with a test set, it's really about estimating how well are we going to do in real life. So keep that in mind. I think that's a lot of people do these kind of things, but really understanding why can help you reason about your real scenario better, and try to can help you kind of stop making some of these mistakes, and they happen fairly frequently. So that's so think about the kind of assumptions that you're making. Think about how is your data generated. So that's important both for how to model your case, but also to think about how is it going to be used later. In that sense, also data availability, though that's already kind of a way to, this target leakage is one way that, yeah, you don't have that available, but there's a lot of other ways, and that's also broader than this topic. Thinking about when is your data available can really help you model things better. And always keep the goal in mind, because that is really what it's all about, right? We're trying to solve this problem. We have this goal in mind, and we need to really properly, fairly evaluate how well we can reach that goal. So that is my presentation. I want to thank you for your time, and you can find me here on LinkedIn or send me a mail.